In IB physics, we will begin our discussion with measurement and uncertainties. To measure something, we compare the thing that we want to measure, which we call the quantity, with something else as the reference, or the unit. As an example, suppose that we want to measure the dimension or the length of this desktop shown here. In this case, the length of the desktop is the quantity. Now, assume we have nothing nearby to use as a reference other than our own pencil. We could use this pencil as the reference, in which case the pencil would serve as the unit. The length of the desktop in this example is 4 times the length of the pencil. However, the problem with this approach is that the measurement would differ if different pencils of different lengths were used. A more convenient way of doing this is by using a ruler. The ruler has a scale of centimeter or millimeter that can be used as the unit of measurement. The idea is that this type of reference could be duplicated easily so that it can be used by other people in different locations. For the same reason, several quantities have standard units so that everyone in the world can compare and communicate the thing they are measuring. There are several standards people use for units, but the one that we use in science is the so-called SI system, which is short for International System of Units. Most countries adopted this system of units, except for a few countries that use non-SI system in their government and industries. And we only have 7 fundamental quantities and units as we can see in this table. We have distance, mass, time, electric current, temperature, amount of substance, and intensity of light. However, candela, which is the unit of the intensity of light, is not the required as a unit in IB physics. What about the rest of the units? The fundamental units are the basis for all other units. In other words, any other units are derived from the fundamental units, and these are known as the derived units. Consider, for example, speed. Speed is defined as the rate of change of distance, and whenever you see the word rate, it usually refers to a quantity over time. So speed equals distance over time. Therefore, the unit of speed is the unit of distance divided by the unit of time, which is equal to meter per second, or m per s. In IB physics, we utilize exponential format. For example, meter second to the power of minus 1. And you are expected to use this format in examination. The dot between meter and second is there simply to avoid confusion when combining units mathematically. The second example is force. The force exerted on an object is defined as the product of the mass and the acceleration of that object, F equals ma. The unit of force is therefore the unit of mass, which is kilogram, multiplied by the unit of acceleration, which is another derived quantity with a unit of meter per second squared. Again, in IB physics, this is written as kilogram meter second to the power of minus 2. In physics, we deal with a wide range of numbers or values, from very small numbers like the size of the electron to very large numbers like the distance between planets. We have two approaches that we can use to simplify small and large numbers. The first method involves the use of metric multipliers. For this approach, we change the unit by using a prefix. The units are defined in multiples of 10 from the standard one, and we'll see an example in a moment. A more complete list of these prefixes can be found in your physics data booklet. The second method is referred to as scientific notation or standard notation. We don't change the unit for this approach. Instead, we change the number in the form of a times 10 to the power of b, where a is a number between 1 and 10, 1 is included, and b is a whole number that can be either positive or negative. Example: a mass of 306,000 grams can be expressed in two ways. First, using metric multipliers, 306 kilograms. This way, the value is more readable. We add the prefix k, which means kilo, to replace 1,000, or 10 to the power of 3. In scientific notation, this value is written as 3.06 times 10 to the power of 5 grams. Note that the unit is still grams, but we changed the number portion of the value so that there is only one digit to the left of the decimal point. Last but not least, we'll talk about order of magnitude. Sometimes we need to make a rough estimate of the value of a quantity. This is done, for example, to make sure that we don't make blunders or mistakes when we enter a number in a calculation. The order of magnitude refers to powers of 10, with each order of magnitude being equal to a multiple of 10. For example, the order of magnitude of 12,000 is 4, or 10 to the power of 4, because writing in scientific notations, 12,000 is equal to 1.2 times 10 to the power of 4. So we refer only to the powers of 10. Order of magnitude is also a common way to compare values. For example, 12,000 is 3 orders of magnitude larger than 12, since taking the ratio of these values gives us 10 to the power of 3.